All right, let's dive into the hidden rules that hold our entire world together. I'm talking about everything from the tallest skyscraper to, the very chair you're sitting on. It's all governed by a core set of construction principles. So let's get into it.
So, have you ever really stopped to think about it? What is actually holding up a massive skyscraper? It's definitely not just brute force. It's this, elegant science that lets us build these incredible structures that touch the clouds and can handle some seriously powerful forces.
Yeah, the answer is so much more than just throwing a bunch of steel and concrete at the problem. It's this really precise blend of a few key things. You've got materials science, the fundamental laws of math, and this is the important part, a really deep understanding of what we as people actually need to feel comfortable and safe inside these spaces.
Okay, so here's how we're going to tackle this. We're going to take a kind of ground-up journey. First, we'll look at the actual stuff we build with. Then, we'll get into the numbers that make it all work. After that, we'll touch on the human element, because that's who it's all for, right? And finally, we'll see how it all clicks together.
All right, first section, the stuff of structures. Let's get right into it. What are we actually building with? And, how on earth do we decide which material is the right one for the job?
You can't just pick a material because it looks good. Every single one is judged against this long list of properties. Of course, their strength, like can you pull it apart? Can you crush it? Can you shear it? But it goes way beyond that. We have to think about things like, will it catch fire easily? How well does it handle heat? And something called embodied energy, which is basically the total amount of energy it took to create that material in the first place.
And this right here brings us to a world of trade-offs. There's no silver bullet. The classic example is timber versus steel. Steel, it's got this incredible strength-to-weight ratio, it's amazing. But it rusts and it conducts heat like nobody's business. On the other hand, you've got timber. It's a fantastic insulator, it's a renewable resource, but it's vulnerable to rot and fire. See what I mean? There's no single perfect material. It's all about picking the right one for the right situation. And speaking of those vulnerabilities, look, understanding how these materials break down over time is just critical. It's a safety thing. For timber, it's a pretty straightforward process, right? You get moisture, that invites fungus or insects to the party, and they literally eat away at the wood, weakening the whole structure. And that is exactly why proper treatment and smart design are absolutely non-negotiable.
Okay, so we've got a handle on the materials. Now let's talk about the invisible forces that are constantly acting on them. This is where things get really interesting, because now we're diving into the math and physics of it all.
And a lot of this starts with fundamental ideas like Hooke's law. It sounds complicated, but here's the deal. It basically lets us predict exactly how much a material is going to bend or stretch when you put a load on it. And believe me, this is not just some abstract theory. This is the fundamental bread-and-butter calculation that tells an engineer whether a beam can actually support the weight of the floor above it.
Okay, flashback to math class. Remember this guy? The quadratic equation? Well, guess what? It's an absolute powerhouse in construction. Seriously. It's what engineers use to plot the perfect, elegant curve of an arch that has to carry a huge load, or to calculate the precise sag in a suspension bridge cable. It's all about making sure every single force is distributed safely and efficiently.
So yeah, construction is just steeped in mathematics. The whole shebang. We're talking trigonometry for surveying the land and getting the angles right. We use something called mensuration, which honestly is just a fancy word for measuring volumes, to figure out exactly how much concrete to order. And we use statistics to analyze all the data from material safety tests. It's everywhere.
But look, buildings aren't just giant math problems to be solved. At the end of the day, they are spaces for people. And that brings us to what might be the most important part of all, the human element. So, what does that mean? Well, first and foremost, a building's #1 job is to manage heat. It's supposed to create this comfortable little bubble for us to live in, whether it's absolutely freezing outside or scorching hot. And to control that bubble, you have to understand how heat escapes. It's like a leaky bucket. Heat gets out through the building's fabric. That's the walls, the roof, the floor, and of course through drafts. We have these things called U-values to measure how good a material is at insulating. And we're always on the lookout for thermal bridges. Think of them as little superhighways for heat, weak spots where it can just sneak right past all the insulation. Okay, next up, sound. Let me tell you, a building can be structurally perfect, it can be beautiful, but if it's noisy and you can't get any peace, it's a failure. Simple as that. This is where the science of acoustics comes in. It's all about managing sound to make a space comfortable.
And one of the key things we look at is called reverberation time. Here's an easy way to think about it. Imagine you clap your hands once in a giant empty cathedral. Now imagine doing the same thing in your cozy, furnished living room. That time it takes for the echo to completely fade away, that's the reverberation time. And learning how to control that is how we design everything from incredible-sounding concert halls to super quiet offices.
And finally, of course, there's light. We have to be able to see, right? Good lighting, whether it's from the sun or from a bulb, is just fundamental to making a space feel good and, actually be usable.
We actually have a special unit to measure light intensity. It's called the lux. All it does is tell us how much light is physically falling on a surface. So, for example, the desk in your office, it probably needs around 500 lux for you to work comfortably without straining your eyes. But a simple hallway, that might only need 100. It's all about designing the light for what you're actually doing in that space.
Okay, so we've got the materials, we've got the math, and we've got the human factors. So what does it really mean to master all these principles? How do you bring it all together?
Well, it's really a journey, kind of like leveling up in a game. You start by just knowing the basic terms and concepts. But real mastery, that comes when you start moving up that ladder. You go from just solving problems to really analyzing and evaluating all the different options. And at the very top, you're making these deep connections between everything we've talked about to come up with the absolute best solution.
So here's a little challenge for you. The next time you walk into any room, just pause for a second. Look around. Think about the materials in the walls. Think about the invisible math that's holding the whole thing up. Notice the way the light falls, or listen to the quality of the sound. These principles of construction, they're literally everywhere, silently shaping the world around you. The real question is, what will you notice differently now?